content-wise, which is to say we're going to flash forward to Chapter 5 and talk about antiderivatives and integrals, and then we'll go back and do Chapters 3 and 4. So, a little bit of a weird order, but we'll see how it goes. Doing things a little bit out of order. Okay, so I think it was either last time or the time before we talked about what the idea of an antiderivative was. All right, so let's just remember that. So function big F is an antiderivative of another function little f, means if you take the derivative of the big F, you get the little f. Okay? No big deal there, right? Then why did I make a big deal about saying an antiderivative as opposed to the antiderivative? What's the issue? Yeah, so we say an, because the function little f could have infinitely many antiderivatives. And we know that it's infinitely many immediately because, let's just say f of x was 2x. Well, give me an antiderivative of that. X squared plus 4, x squared plus 7, x squared plus any constant. Okay, so hence, there are really infinitely many answers to the question. However, like, in what sense are x squared plus 1, x squared plus 4, x squared plus pi, all of those guys, like, yeah, they're different, but they're kind of the same too, because what's the only thing that makes them different? Yeah, the constant part. What's the same about them is the x squared bit. Okay, so so there's a theorem then. Sorry. That any two antiderivatives are basically the same with the exception of that constant part, right? So one of them is a constant plus the other one, and the constant could theoretically be any number, okay, but it's a real number. Okay, so so if we look back up at our little list for the example, x squared plus 1, x squared plus 4, x squared plus pi, and so on, right? There are infinitely many things there, but they're all basically the same. The only thing that is different between all of them is what the value of that constant is, okay? And so what we'll say is that x squared plus a constant is the antiderivative of x squared, or sorry, 2x. Okay, so here I'm using the definite article the, right? And I'm justified in doing so because x squared plus c encapsulates every possible antiderivative. Okay, so another way we might say that it's the most general thing that I could write down. Right? Now, what is c? I don't know. It's some number. Okay? Okay, does that make sense? Just lingo-wise. Now, from a graphical standpoint, right, so let's go back to my little list here of the examples. X squared plus 1, x squared plus 4, x squared plus pi, and so on. What do those look like if I were to graph all of them? Well, what shapes would I get? Yeah? Bunch of parabolas. Okay, because they've all got the x squared bit. Okay, so that's fine. But what does the plus 1 or 4 or pi or whatever do to it? Yeah. Okay, so in this case, because it's plus a constant, is it up, down, or left, right kind of change? It's up, down, right? Okay. It would be left, right if we had the addition or the subtraction on the inside of the function, whereas here it's happening after we square. Okay, so yeah, these are all the same, except they're shifted up and down from each other, right? So if I were to graph a bunch of them, and if you'll pardon my, terrible art skills as usual, right? If I have, for example, x squared plus 1 here, x squared plus 4 is the same shape, just shifted up 3 more units. Okay, so they all look the same with the exception of the vertical shift, and that's being reflected by that plus c, right? Because plus a constant gives you a vertical shift. Okay, so does that make sense? No. Okay, so let's look at this giant table that's on the sheet here, okay? Theorem 5.1.2. This table, we just sort of snipped it out of the book because it would be a giant pain to type all of this. Okay, so, oh, sorry, actually, before I do that, one other thing. Mathematicians are lazy. You guys have probably learned that by now. And so I don't want to have to sit around and write the antiderivative of blah is blah every time I do one of these. Okay, so what we want to do is introduce a symbol that basically is like similar to the d over dx symbol that meant take the derivative of whatever, right? We want to come up with a symbol that means to do anti-differentiation. And the symbol that we've chosen is the following. Okay. This is sometimes called the indefinite integral, and we'll talk about why in a minute, or next time, the integral part of it. So just think of the little elongated S shape, and the dx is kind of they encapsulate the function that you want to anti-differentiate. And the dx, well, or the x specifically, tells me what's the variable. Okay, so that's kind of like if I asked you what's d over dx, you said, oh, x is the variable, I want to take the derivative. If I said what's d over dt, you'd say, oh, well, I want to do the derivative, but now t's the variable, right? Same idea, just which letter is the variable, okay? Okay, so that's the symbol that we're going to use, and the symbol as, or the symbols, I guess, unless you've seen some calculus before, this looks totally stupid. Like, why on earth would I write it like this? And there's a good reason for it, but that's going to be like 2 or 3 classes down the line before all the mysteries are revealed. Right? And if you have seen calculus before, you kind of know where this might be going, but yeah. Okay, so that's just, for now, let's just think of this as a shorthand notation that replaces the long and awkward English phrase, take the antiderivative of blah, okay? All right, so let's take a look at the little table on the sheet there, okay? So there are 28 entries. Down the left are all of the common derivative rules, okay? So all of those we've talked about with, I think, maybe one brief exception. We never talked about number 13. Basically, what's the derivative of, if you've got 2 to the x or 7 to the x, right, it works kind of like e to the x, except with this one minor little tweak. Okay, that's not really a big deal. But the rest of them are all the basic ones that we've talked about, right? So what's the derivative of a constant? That's number 3. 0. What's the derivative of x to a power? Yeah, n times x to the n minus 1 if the power was n. That's number, what, 5 on the sheet? Okay, then we've got all the trig function dudes. We got e to the x. We got the logarithm. Okay, so these are all basic derivative rules for the basic sorts of functions that we need to deal with. Okay, and then there's a couple, there's one in here. So take, for example, numbers 1 and 2. Well, let's actually start with number 2. If I want to take the derivative of the sum of 2 functions, what do I do? What can I do instead? Yeah, or I could take the derivative of each one, add up the answers, and I get the same thing, right? Okay, so the derivative of a sum is the sum of the derivatives. Works the same if it's a minus sign, as long as you keep the order set. Constant multiples, that one's number 1, right? Derivative of a constant being 0, right? So these are all the basic rules. Well, most of the basic rules. Okay, what's missing from this list? Product rule, quotient rule, and chain rule. Okay, for good reason. Not that it's bad to leave them off our derivative list, because we've certainly talked about them. Okay, but let's look at the other half of the list here, right? So we've got another 14 things going down the right, and all of these 14 things are basically the antiderivative version of the 14 things that are on the left. So let's take, for example, number 3 on there, both number 3s, okay? So if the derivative of a constant is 0, what's the antiderivative of 0? A constant, okay? All right, so let's take the number 4. If the derivative of x is 1, what's the antiderivative of 1? X plus another constant, okay? Let's pick another one. Well, like, let's say number 6. All right, if the derivative of sine is cosine, what's the antiderivative of cosine? Sine plus a constant, okay? All right, so you guys see how these are kind of working back and forth? And in a sense, with the exception of that pesky constant, you can think of derivatives and antiderivatives as being inverse processes, okay? So in the same way that, like, addition and subtraction undo each other, if I take the derivative of an antiderivative, what happens? I get the same thing back, right? So it's almost as if they cancel, and I'm using big old air quotes there, okay? Now, the one exception to that, of course, is this annoying little plus c, but what's a constant amongst friends? I mean, not really the end of the world. Okay, now, let's look at one that's maybe not quite so obvious. Let's take number 5. Okay, so the derivative version of number 5 was this. Okay, the derivative of x to some number is Power comes out front, x stays the same, take 1 away from the exponent. Okay? So what we need to do is we need to think about what's the inverse process to that. Okay? All right, so forget calculus for a moment. You're all wearing shoes, right? And probably most of you are wearing socks beneath said shoes. Yeah? How did you put those on this morning? Yeah, you put your socks on, and then you put your shoes on, right? Doesn't really work if you try and do it in the other order. Okay, great. Now, end of the day, you get back to your dorm room, you're going to remove said articles. How are you going to remove them? Shoes first, then socks, right? If you try and pull the socks off first when you've still got the shoe around them, unless you got a pair of scissors, that ain't going to go so well, right? Have you ever actually thought about this, like in a mathematical sense? No, you just want to get the dang things off. Right, so if we have a process here, namely the process of putting on socks and shoes, that requires 2 steps, and they have to be done in the correct order, right? Socks first, then shoes. The reversal of that process, well, what's the opposite of putting on a sock? Taking it off. What's the opposite of putting on a shoe? Taking it off, okay? So not only do I need to invert each of the individual processes, but I need to reverse the order in which I do them, okay? Right. So what are the 2 processes that I did here when I took the derivative of x to the n? The first thing I did was multiply by the old exponent. The second thing I did was I took 1 away from the exponent. Okay? So what was step 1? Okay, so those were my 2 steps, like putting on a sock and then putting on a shoe. Okay? So if that's the case, what should the inverse process be? Well, what's the opposite of multiplying by the old exponent? Dividing by some sort of exponent. Okay, now I was very careful here to write old. What's the opposite of old? New. Okay, so multiply by the new exponent, and then what's the opposite of subtracting 1 from the exponent? Adding 1 to the exponent. Okay, so if I want to do this, what should my steps be? Or, sorry, I wrote this backwards. Let's try this again. Okay, what's step 1 if you're taking off your shoes and socks? Add 1. Okay, take off your shoe. Okay, so step 1 is add 1 to exponent. And then step 2, what's the opposite of taking off your sock? Or, sorry, putting on your sock? Taking it off, which in this case would be divide by the new exponent. Okay, so if I add 1 to my exponent and then I divide by that new thing, and then of course I've got a plus c. Okay? All right, does that make sense? Right, the socks and shoes sort of analogy. Okay. There's just one minor problem here that we need to contend with. What minor problem might I have with the answer I just wrote down? Yeah, exactly. What happens if I had started with the value n equals -1? Then what? This formula doesn't make sense. right? Because I'd be dividing by 0, and that's verboten, right? You see what I did there, Owen? Yeah. Okay. So, let me write this. So, this exponent rule is valid provided that the original exponent was not -1. Okay, which begs the question, what do we do if it is -1? Throw up our hands and quit? Of course not, right? It turns out that, yeah, use a different rule for that one. So what we're really doing here for the n equals -1 case is we're asking what's the derivative of 1 over x, right? Because remember, what does x to the -1 mean? It means 1 over x, right? Same thing. Okay. Now, remember, too, that antiderivatives, we should understand them because, or at least to start with, because we know all of our derivative rules, right? And what this is asking is find me a function whose derivative is 1 over x. Do you know such a function? You damn well better, for two reasons. One, because you've been in this class for a semester, and two, it's right in front of you on the damn sheet, right? Okay, so what function am I looking for? Yeah, the natural log. All right, now, there is one pesky little detail. If we want to get really technical, there should be an absolute value here, okay? For long reasons that I don't really feel like getting into at 8 in the morning, and you guys probably would forget by the time you walked out the door. Trust me, I'm a doctor. It has to be there. Okay. That said, am I going to crucify you if you forget the absolute values? Probably. No, I won't, right? Just put them there, please, humor me. But there, like I said, there's technical reasons why we need it, and maybe later we'll talk about why it needs to be there. But anyway, so yeah, the derivative of natural log is 1 over x, right? So what's the antiderivative of 1 over x? The natural log. Okay, what are the two sort of details here that are annoying? Well, yeah, we got the plus c as usual, and that silly absolute value. Okay, just do it. Okay. Although in many cases it doesn't actually matter, but to be correct, we'll just write it there. Okay, so there's that one pesky exception. Okay. So let's see. That gets us number 14 on the sheet. And the rest of them should be pretty straightforward, right? They're just sort of the opposite of whatever was on the left-hand side. Okay? Where this can get a little bit annoying, though, is look at all the trig function ones. Right? What's the derivative of sine? Cosine. What's the antiderivative of sine? Negative cosine. So you got to be careful, right, with the trig functions, particularly sine, cosine, to not botch the negative sign if it needs to be there. Okay, that comes with practice. Another way that you can kind of think of it is this. So let me draw a little bit of a chart. Okay, what's neat about sine and cosine, right, is if you take the derivative 4 times, you get back to where you started. Okay, and So the derivative of sine is cosine. The derivative of cosine is minus sine. The derivative of minus sine is minus cosine. The derivative of minus cosine is back to sine. Okay, so they kind of go in a nice circle. Well, what about if I want to do clockwise for differentiation? Then I go counterclockwise or anti-clockwise if you're British. To do integrals. Actually, here's a really fun one. What's another word for anti-clockwise or counterclockwise besides those two things? It's really archaic. Starts with a W. No? Widdershins. Anybody ever heard that word before? You have? When? Oh, well, okay. Yeah, so it's sort of an archaic English word for counterclockwise, Widdershins. So there's your SAT vocabulary word for the day. How about that? Okay, so, right. Now, then the other ones that we've got, so numbers 8, 9, 10, and 11, right? You know, it's sort of funny that I found that, let's take number 8, for example, integral of secant squared. That being tangent, like if I asked you what's the derivative of tangent, you'd all be like, oh, secant squared, no big deal. But if I turn around and ask you what's the antiderivative of secant squared, then I get a whole bunch of doo-doo-doo, right? Even though it should be obvious, right? So, right. Okay, so just think for a minute. Sometimes these are really easy. They're just things that we've committed to memory, calculus students, and we don't want to get beaten with Dr. McKinney's stick, right? Although we have a few guys who aren't so dutiful. Kids these days. Anyway, yeah, I'm talking about you, Mr. Silas. If you're there on Twitch, I got a meter stick with your name on it. So, okay, good. Then there's a couple more that we need to talk about, which is, so what did we talk about, I guess, was it Wednesday last week? We did derivatives of inverse trig functions. Okay? For example, we talked about arctangent. Dang it, come on. There we go. Okay, what was the derivative of arctangent? Not quite. Okay. The square root ones had minuses in them, but that was arc sine. Right, this one, okay? Now, what happens if you forget it? Could you rederive it if necessary? Right, how did we derive that in the first place? What did we do? We said, oh, well, if y is arctangent of x, then that means x is tangent of y. We did some implicit differentiation. We drew a triangle. We did a little bit more work, and then bam, we eventually got 1 over 1 plus x squared. Okay, good? All right, so if that's the case, what is the antiderivative of this? Arctangent of x plus our constant, right? Okay. This is another one that I found that when you first look at it, like, okay, in this moment, given that the derivative of arctangent is written directly above the question, it's pretty obvious. But, you know, when you find yourself doing homework or an exam or something like that, and you come across the antiderivative of 1 over x plus 1, then you're just like, I don't know. You're reduced to a puddle of confusion, even though it should just be sort of automatic, okay? Right. Now, I should mention that for the inverse trig functions, like, what was the derivative of, for example, arc sine of x? It was that, right? And arc cosine was the same thing, but with a minus in front. Okay. Do I want you guys to memorize those? Probably. Probably not. Okay. For reasons that will become clear if you take Math 112, the only one that actually you have to memorize per se is arctangent. Okay. So that's the one I want you guys to know off the top of your head. Arc sine and arc cosine, don't worry about them. If you need it, I'll give it to you. Yeah. Now, I suppose, I mean, there are situations where having that committed to memory is kind of useful. For example, in physics or astronomy or something where there's going to be lots of arc sines flying around, you'd probably just sort of memorize it by osmosis. But yeah, arctangent is the one that we really will use a lot for long reasons. Okay, so, and then of course arc cosine is sort of the same idea as arc sine, it's just got a minus in front. Okay, so does that get basically all of the basic functions that we've worked with? Right, we've got the logarithm, we've got the trig functions, we've got the inverse trig functions, we've got e to the x, and we got x to powers, and we know what to do with sums and differences and if there's a constant multiple, right? So what's missing? We already said product rule, quotient rule, chain rule. Those three are missing. Anything else missing? And product, chain, and quotient rule being missing, that's kind of a big deal, right? That's a lot of stuff. Okay, so the quotient rule is really just a special case of the product rule, right? Because if I want to think of f over g, couldn't I think of it as f times 1 over g? Well, then it's a product, not a quotient, okay? So quotient rule, let's throw him out, right? Because he's not special. So that leaves product and chain rule. The chain rule, how you do it in reverse, we'll talk about towards the end of this chapter, and that's this method called U substitution. So we'll get there. Okay? Huh? Are you about to be the nope octopus out the door? Yeah? Okay. You know, I wish I could have, like, I don't know, did I show on my phone when I have, like, the thing with the buzzer and a few other noises? I wish I could have, like, a little screen where, like, it's like a meme screen. Actually, I could do it with my Elgato, where just, like, a meme will appear on the screen and then disappear. I can do that. Okay. Right, so the nope octopus. So we'll talk about how the chain rule works in reverse towards the end of this chapter. How does the product rule work in reverse is a thing called integration by parts, and that's the very first topic that you learn in Math 112. Okay? So, Mr. Burns is having a, nervous breakdown over here. Yeah. So, yeah. So those of you who are going on to Math 112, all the mysteries shall be revealed then. And if you're not going to go on to Math 112, think of it this way. You're going to live in perpetual ignorance for the rest of your life. Yeah, well, that's sort of a personal judgment. So anyway, okay. So we've got about, 15 minutes left, roughly? Little shy of that. So I'll quit the stream, and let's just work on these 4 problems here. kind of go through them and think about how they're going to work. Okay? Does that make sense? And I'll come around and menacingly threaten you with a stick. So so look at these four, and let's just get our brains moving. All right, so I'll quit the stream here.